we are talking about the momentum equation so far. So this momentum equation usually, if we consider the viscosity, usually they will regard as the Navier-Stokes equation. So, but if we simplify, now we come to the Euler equation or the Bernoulli equation. So far, any question? So in the momentum equation, basically we are talking about the force. Acceleration is due to the external force. So so far we are talking about this force. Mostly is on the surface force, contact force. In the future, if you want to consider more complicated problems, for example, right now there are many digital devices. If you want to consider some kind of like electronic force, or sometimes electronic we use like magnetic force. If you want to consider some additional force, this kind of momentum equation can be rewritten. Okay, so so we continue to talk about this momentum equation.
consider equation 2.27 is wrong. The Middleton shear trend is one of the two, so the solution become
Is
here, the Middleton. Because the shear trend's formula is one of the two.
one.
Joe.
Okay. You are right. It is.
Yeah.
So basically from the Navier-Stokes equation, I think this is some kind of like a difference from the undergraduate class to the graduate class. Basically, in the undergraduate, usually Navier-Stokes equation just give you the final result. But here in graduate class, we will talk about how they propose this hypothesis to get this result. And from here, last week we talked about the surface force component is like this. So we talk about their assumption, their theory, but the final result for this is for us to substitute into the Newton's second law. Newton's second law is acceleration due to the external force. So for the body force is the gravitational force. In case if you are in the electronic field, then you maybe have additional electronic force. Then surface force, if we substitute into this equation, basically we will use diverge. So diverge, they will cancel out one direction. So which direction we will cancel out in the stress. Usually this is very common. For many students, maybe it's confused. Even for this book, also, it's confusing as well. So I need to point out. Okay. So because in this book, for example, the stress definition, then we have force direction and the space direction. In the stress, we have force direction and on which surface we are acting on this surface force. Okay? So in the definition for this book, for example, definition of this book, equation 250, I is defined by the area or defined by the force direction. Anyone have an idea? Okay, so doesn't matter because in many different textbooks, maybe they have a different direction. One is you action on which surface. The other is the force direction. But for the diverge, which direction we are going to cancel out? You think it's a surface?
Surface.
Yeah. So stress.
Oh, yeah.
Stress. If we have a stress, normal force and shear force, and the normal force, then we have same surface direction because they are acting on the same surface, right? But force direction are different. So this is the question I asked. Which direction we're going to cancel out? You think it's the surface? Doesn't matter. I didn't count the score, right? You see the force. Okay, you should think about acceleration, right? Acceleration is your acceleration that have a direction, and this acceleration is due to an external force. So the final part, this should have same direction as acceleration. Similar to the body force should have same direction as acceleration. If you don't have a force in this direction, there is no any possibility to have acceleration. So basically, this is a cancel out the surface direction. So if you action on the x surface is the normal force is in the x direction, and the shear stress is in the y and the z direction. Okay, so this is what I mentioned. This is a little bit different from the equation 250. Okay, but here we just want to keep the force direction in the final result. So for example, body force, the only possible in acceleration in the gravitational direction. There's no way in the xy horizontal direction there's any acceleration due to the body force, because your body force only in the gravitational force direction. Then your surface force, that will depend on your surface in which direction. For example, your pressure in which direction, they should cancel out this the surface direction. They only keep the I, because your I must equivalent to the Z, then this term we keep. Okay? So here you can see I is a free index. So if we rewrite this equation, that means we can rewrite the equation like this. So that means in the x direction, for example, I equivalent to 1, then that's in the x direction. X direction will depend on x direction if they have a gravitational force or not. If not, this will come to 0. If they have, then this will be contribution to this one. Similar to the pressure in the x direction, do they have a pressure difference in an x direction? If they don't have a pressure difference, this will become to 0. If they have a pressure gradient, that means in x direction they have a pressure difference, then pressure will cause some kind of acceleration. Similar to the stress. So the stress, if you make it a simple form, it's like a shear stress. But if we write down like a complete form, that will be like the viscosity, if they have some velocity gradient. The velocity, if they have a different, cause some kind of shear strength. Then this kind of shear strength will cause this kind of shear force, okay, or the viscosity force. Second viscosity, usually we don't consider because the continuity equation we satisfy for this for most of the case. In this class, we don't talk about second viscosity. In case if you are consider the compressible flow, very high speed, for example, if you want to make some kind of space rocket, then this kind of rocket with a very high speed, right? This term should be considered, but in this class, this part we don't consider. So for the shear stress, usually we only consider this. If velocity has some difference with the neighborhood. For example, like a boundary layer, they have a velocity gradient. If in the free stream, usually discuss it with this field. Okay, because they don't have a velocity gradient. Okay, so from here, I think it's some kind of like a review index notation, and I like to emphasize your acceleration should consistent with your force direction. Okay, and your force direction include body force direction, their force direction, and the service force. Especially the service force, they have two directions. You should keep the force direction in the final result. Okay? Any question? So I like to emphasize here the force direction should be consistent with the acceleration direction. So that's why this diverge, we cancel out the surface direction, that's space direction. So you must keep the final result, force direction, consistent with the acceleration direction. Okay? So here, the acceleration direction and the force direction, we are using I pre-index to represent the force direction. Okay? And the J is correspond to the area or space, which area we are actually that direction. Substitute this into the final result, and if we in the incompressible flow case, then we will have a more simplified equation. For the incompressible flow, the density is constant, same as the volume. So we will have a continuity equation like this. This is we talked before in the mass conservation equation. And in the incompressible flow, if we substitute that force into this equation, the final term with the second viscosity, they will disappear because the continuity equation. Another term in the viscosity, we can rewrite like a Laplace. Usually, this form is your undergraduate Navier-Stokes equation. Acceleration due to the computational force, pressure difference, and viscosity force. And this viscosity is due to a Laplace operation. But how come from here you will get this kind of Laplace operation? But your Laplace only this term, right?
No, Laplace is written. Laplace is written. That is scale.
That's here. Laplace. If we take a Laplace, say it's the Laminar index. So for example, if the Laplace for the x direction, u, then here we will have x direction velocity. But this term is a dummy index, so we will have Laplace x squared differential, y squared differential, z squared differential. It's only this term. But how come this term is here? Maybe we can correct. You can think about why from this force, and after we use this equation, we substitute into a momentum equation. Viscosity force, why they will simplify to this term? Because this term usually you undergraduate case. And they have some assumption. One is the density is a constant. Then we can use this incompressible flow. And another mu is a constant. So viscosity is a constant. So we can take that as the, if the viscosity is not constant, they are function of a space, then that will be another story. That will become more complex. But even right now, why this can simplify to the undergraduate episode equation under what kind of assumption? You must have some kind of assumption that you can simplify. So we take away, after break,